Okay, hello everybody and welcome to Unit 7, Day 8. For Unit 7, Day 8, the last day of Unit 7, we are talking about the locus definition of a parabola. So I feel like at this point we know a lot about quadratics, and today we're going to look at a really different approach and a way of defining a parabola. So let's actually get started by writing down a quick definition of a parabola in the notes today. A parabola is defined as being the set of points that are equidistant from a fixed point, which we will call the focus, and a fixed line, which we give the special name the directrix. So parabola, set of all points that are equidistant from a fixed point and a fixed line. And in fact, for any of the parabolas that we've sketched so far, if we can identify this fixed point and where this fixed line are located, all the parabolas that we've looked at to this point meet that criteria. That if we identify where the focus and the directrix are located, all the points are equidistant from those two things. So let's get a quick visual of what we're talking about here. So if we just maybe make a quick set of axes here, and I'm going to choose, just for simplicity, a vertex point at the origin to get started. I'll say that if I go up a few units from the vertex, I'm going to call that the focus, point F, that according to our definition, we have to go in the same distance away from the vertex and draw a line here. And this horizontal line that I'm drawing in is, I'm going to label capital D for the directrix. Okay, so far all of the points that we've drawn here, just that singular vertex on the parabola is equidistant from the focus and the directrix. And just for pattern purposes, what I'll say is, if I go out, it looks like on my grid I've chosen a distance of 2 units here. If you've chosen a different amount, that's fine. But if I go 4 units in each direction from the focus, we can sketch a nice sketch of this parabola. And like I mentioned before, if I were to pick any random point and find its distance from this fixed point, the focus, that distance right there has to match the distance straight down perpendicular to that directrix line. Okay, any point on this parabola would meet that criteria. Now, a couple key notes about what I've just sketched in here. In general, I'm going to identify the distance that I've determined from the focus to the vertex here as P. Okay, so that distance I'm going to label as P, which also means that the distance from vertex to directrix can be indicated as P as well. And something that's kind of unique, now I already chose these points for us here, but this distance from this point on the parabola to the focus, and same thing going this way, each of those has a length of 2 times whatever P is. So when we're sketching parabolas, we can be a little bit more accurate about our sketch by including those, I'll call them accuracy points for now, but they actually do have a special name. So in total, this segment right here that I'm going to draw through the focus, it's kind of parallel to that directrix line, that segment has a length of 4P. Okay. So if we then connect this to, well, what's the equation of the parabola that I just sketched? I'm going to bring this to the next page here. So the equation of that parabola that I just sketched is going to follow the form that x squared equals 4py. Okay. So in this new form, this locus definition of a parabola, p is going to be the distance from the vertex to the focus, just like we labeled it in the diagram a minute ago. P also happens to be the distance from the vertex to that special line called the directrix. So the value of P will be important to us as far as when we go to make a sketch given in a parabola in this form. And that segment that connected to those accuracy points that I mentioned a moment ago has a special name. I'm actually going to, in our notes, define it as the length of 4p, Now keep in mind there are certain special cases where P could be negative, so I'm going to toss some absolute value around that. The absolute value of 4P, that segment that we've sketched, has a special name. It is called, it has Latin roots, it's called the lattice rectum. I realize that's a weird name. So really from this point forward, we're going to abbreviate that segment as the LR. Okay, so typically I'll say that that's not the most critical piece of what you'll be asked to identify. We definitely want to know the vertex, the focus, the directrix, but to be a little bit more accurate about our sketch, we will include the endpoints of the LR when creating sketches. One thing I will mention as well is that there are some other cases that we can consider. So by the way, this parabola up here definitely has a vertex at 0, 0. We'll explore some cases where that's not the case later on. But I'll tell you that if we keep the vertex at 0, 0, but I change the equation to x squared equals negative 4py, it wouldn't be too much of a surprise to you that when I sketch x squared equals negative 4py, we still have that vertex of 0, 0, but this is a parabola that opens down. Okay, so we get some sort of focus, some sort of directrix line, all the points are equidistant from those two things. So there's a case for a parabola that opens down. And then this is going to be probably the coolest part of today's lesson, that not only do we have a parabola that opens up like the first one, and then this one that opens down, but get ready for this, we have y squared equals 4px. When the variable's y is squared, what's going to happen is essentially we're talking about thinking about the inverse of what we started with originally. So if you take that and think about in your mind flipping it over y equals x, you're now going to get a vertex at 0, 0 that opens up to the right. Okay, so we get a focus, we get a directrix line. So all the points on that graph would be equidistant from those still, but this is a parabola that opens up to the right. And if we got a parabola that opens up to the right, you guessed right, we get a parabola that opens up to the left if the coefficient of x is negative on the right side. So if I could squeeze the sketch in here, opening up to the left, here's my focus, here's my directrix. And there we go. These are really the 4 cases we're going to analyze today. So I think at this point, let's actually get into some practice with sketching these. So if I gave us the example, x squared equals 8y. Okay. So first and foremost, the first thing I would do is maybe let's identify the value of p right away. So remember, this number right here in the equation is equal to 4 times p. So if 4p equals 8, then p definitely equals 2. This right now is a parabola whose vertex is at 0, 0. And I know that based on the equation x squared and that p is positive, it's going to be a parabola that opens up. So it's going to be something that looks like this at the end. Okay. In fact, actually, let's start making a sketch over here. It's not really a good vertical line there. Let's try that again. All right. Not much better. It's all right. Okay. So once we draw the x-axis here, let's start with our vertex at 0, 0. And based on my value of p equaling 2, I know that if I go up 2 units from the vertex, label that v and this point f, that's going to be the focus. And if I go down 2 units from the vertex, that this horizontal line is the directrix. In a minute, we'll list those coordinates and the equation of that line. But the last thing I want you to remember is those ends of the LR, the ends of the lattice rectum. If p equals 2, if you double that, which is 4 units, that's how far in either direction from the focus we would go to sketch the parabola. Okay. So there's a pretty accurate representation of the parabola. So remember, this distance in general is p. This distance to each endpoint of the LR is the length of 2p in that case. So really quickly here, the focus of this particular parabola, because these are things we'll be asked to identify, would be the coordinate 0, 2. The directrix has the equation. Let's say it's a horizontal line down 2 units, so y equals negative 2. Okay. And finally, if we want to talk about the LR, the lattice rectum has a length of 8 in total. That's the total length of the segment that connects those 2 points, the segment that connects through the focus. And then the ends of the LR, in case we want to list those coordinates specifically, We go to the left 4 and up 2, so negative 4, 2. And then also to the right 4 and up 2, so positive 4, 2. So really, these are really the most critical pieces of information that will typically be asked to identify. But certainly this information over here is important in terms of just sketching an accurate parabola, so it is something that I would like you to think about when making sketches here. Okay, let's try a y-squared equation just so we get used to what that feels like. So if we take a look at y-squared equals, let's try 16x. Y squared equals 16x is a parabola that still has a vertex at 0, 0. If I find the value of p, remember that this number here is what 4p equals, so therefore p must be 4. And just thinking about this standard form here, I can know that if it's y squared and p is positive, it's going to open up to the right and eventually look something like that. Okay. So if we go ahead and start our sketch here. Erase this for a second. Okay. So we're going to have, it's very tough on the screen, guys, sorry. I apologize for my shaky y-axis there. All right, here's my vertex. My focus is going to be 4 units over from there. So here's my focus, it's going to open up to the right. I like to think of it as, it's kind of maybe a weird reference, but I think of the parabola as like a little Pac-Man, if you know the game Pac-Man. And the parabola likes to eat the focus. I think of my little parabola Pac-Man eating the focus. If I go 4 units to the left this time, that's going to get me this vertical line, which is the directrix here. So if we think about how to get to those accuracy points, the accuracy points would be 2p away from the focus. Now I realize doubling p gets me a value of 8, and that's going to be tough for me to fit in here unless I make maybe some little quick scale and say, hey, that's 2, 4, 6, 8 on the y-axis. And maybe I'll do that just so that we can squeeze this in here. There should be negative 8 down here. So those are the ends of the LR. And the parabola is going to eat the focus and open up to the right. Okay. So really quickly, the vertex, we said 0, 0. The focus is at 4, 0. We went 4 to the right. The directrix, keep in mind, just be careful here, is a vertical line now. So the vertical line has an equation x equals, and if I go 4 to the left, negative 4. The length of the segment that connects the ends of the LR is 16. And if I wanted the endpoints of the LR, I went to the right 4 and up 8. And we went to the right 4 and then down 8. Okay. If at any point during the video something's going too fast, feel free to pause and take a minute and catch up. And certainly you'll be getting more practice with this later on in class. Okay. I think we're really ready to change some things up here and move away from the origin a little bit. So for our third example here, let's consider the case for this parabola. We have x plus 3 squared equals negative 12 times y minus 2. Okay. So this is a parabola that clearly doesn't look exactly like the standard form that we started with today, but it really just represents a shift from x squared equals 4py, if we think about that. In fact, if we're looking at this form right here, hopefully you can see that the shift, that if I have plus 3 here and I have minus 2 over here, that the vertex coordinates, similar to what we've done with circles and some other conic sections that we've discussed, the vertex would be the point negative 3 comma positive 2. And then the rest of the process pretty much follows the same idea, that if I shift the vertex to negative 3, 2, this negative 12 here still represents the length of 4 times p. So if 4p is equal to negative 12, that tells you that p equals negative 3. If p is negative, what I'm hoping that means to you in your mind is x squared is one of those that's going to open up or down. But when p is negative, we're definitely getting a graph that looks like this. It's going to open down in this case. Okay, so before I actually even find some of the other important info, like the focus and directrix, let's start with negative 3, 2. Now, you can draw the axes, remember, wherever you want if you have some graph paper here. So maybe I'll shift my axes over a little bit, because I know negative 3, 2 is going to be this point in quadrant 2 over here. And using my value of p to get to the focus, we're going to have to go down 3 units. So actually, once I plot that point, it might be nice over here to list its coordinates. So that would be negative 3, negative 1 for the focus. And if I go up 3 from the vertex, That's going to get me the directrix 1, 2, 3 up here. So that's this line right there. Capital D for directrix. So the directrix has the line back to being horizontal. So we're at y equals 5. And then finally, if I go ahead and get some accuracy points here, remember P has a value of 3, or it doesn't matter that it's -3 in this case. If we double that and go out 6 in each direction from the focus, it's going to leave me a little bit off the grid here. That's okay. The parabola that opens up pretty wide there to get to those accuracy points or the ends of the LR there. Just keep in mind that we define the lattice rectum today as being the absolute value of 4P. So in this case, the lattice rectum has a length of 12. And the ends of the LR are from the focus, right? We have to go to the right 6 and to the left 6. So if you can just look at those coordinates right on the grid as they appear here, but we would have 3, -1 is one endpoint, and then 6 to the left would be at -9, -1. Okay. So really not that different if we shift the vertex somewhere else. The value of P is still the same, and the way we calculate all of the critical info to make the sketch is really a lot of the same here. Okay. One last really new piece, just like we've done with circles prior to this, sometimes the equation will not be given to us in this new standard form already. So for example, if I gave you y squared minus 6y minus 20x minus 51 equals 0, well, you know, that look right now doesn't tell me anything about what that parabola looks like yet. So what we're going to have to do in this case is, I'm sure you're guessing it, complete the square. So when you complete the square, what I'll tell you is whatever the squared variable is, and for a parabola there only will be one, we're going to keep the squared variable on the left side and anything that goes with that. So for example, I want to group those y terms together on the left, and then anything that doesn't have or relate to y, meaning the x term and the constant, those are going to get moved to the other side. So the next step, we'll have y squared minus 6y equals 20x plus 51. Add those over carefully there. And then from there, now we can complete the square on the y's. So we get y squared minus 6y plus, well, if we're good at completing the square by now, we've done it a lot, you would have plus 9 there. Do the same thing to the other side, add 9. The left side now factors into y minus 3 squared equals 20x plus 60. And we're very, very close to having this to be a standard form that we're familiar with, but the last and final step would be to whatever the coefficient of x is on the right side, or if this is an x squared equation, whatever the coefficient of y is, you must take that out as a GCF. And luckily 20 goes into 60 nicely. We're left with x plus 3. Now I can see, hey, this is a parabola in a standard form that I'm more comfortable and more familiar with. Okay, so in this standard form, I can clearly say the vertex is, well, you just have to be careful here that in this form, when I get the coordinates of the vertex, we have to get the x value of the vertex from the x set of parentheses. You have to get the y value of the vertex from the y pair there. So although at a first glance it looks like it's at positive 3, negative 3, it's actually the reverse of that. Negative 3, positive 3. Okay, so make sure you go from the x pair to get the x coordinate, the y pair to get the y coordinate. Okay. From there, everything else should follow pretty similarly. That in this case, if 4p is equal to 20, that p equals 5. P is a positive number, and y is being squared. So as a reminder, that means that this opens up to the right. It's going to have a general appearance that looks like that. So let's actually start by plotting that vertex at negative 3, 3. Okay, which is again in quadrant 2. And then from there, we can go 5 to the right and plot the focus. 1, 2, 3, 4, 5. All right, so there's the focus. Here's the vertex. The only issue here being that, you know, this is going to be a parabola. If you think about doubling P and getting 10, those accuracy points are going to be pretty far away from the focus. Okay, so if I go 5 to the left, in fact, my directrix is sort of way out here. 2, 3, 4, 5. It's this line, technically, if I'm trying to be accurate about scaling. Now, oops, I went a little too far. Hang on. Okay. So when I go to plot those, the ends of the LR here, I won't really be able to fit them nicely on the scale that I'm using here. So I'm just going to say, hey, my parabola opens up to the right, and this is fine as far as accuracy goes for now. I realize that those wouldn't hit at the exact coordinates unless I make some sort of scale for the y-axis, which we could easily do. But let's just list some of the other critical info, that the focus would be to the right 5 units, so that would be the coordinate 2, 3. The directrix came to the left 5 from the vertex, so that's going to be x equals, in this case, -8. And if the LR has a length of 20, I would have to go up 10 units and down 10 units from the focus to get to those endpoints. So from the focus, which was 2, 3, up 10, would have an endpoint of 2, 13. And down 10 from there would be the point to -7. Okay. So we're in a pretty good place at this point. The last thing that I really want to do to close out some of this information with parabolas here is talk a little bit about how would I work backwards with this information. So what I mean by that is if I gave you some information about the parabola, could we come up with its equation? All right, so if I told you, hey, the vertex is at 0, 0, and the focus is at 0, -3. I won't make us sketch the entire graph, but I do think there is some benefit to sketching part of what's going on here. So if here's my vertex and go down 3 to get to my focus, I can see a lot of things here that would help me get my equation. One of those things being, I can clearly see that this parabola, in order to eat the focus, is going to have to open down. So that to me is saying, all right, we need an x-squared equation. The other thing I can see is that the distance from the vertex to the focus is 3, so that's my p-value. Remember, if it's opening down, p is definitely negative. And with the vertex at the origin, the general form is going to be x squared equals 4py. So to work backwards here, the equation would be x squared equals 4 times p would be -12y. This is a parabola whose vertex is at the origin and has a focus at 0, -3. Okay, let's try another one quickly here. So if the directrix is at x equals 2, and the focus is at -2, 0. Although maybe you can visualize this without plotting everything. Doing some quick graphs off to the side. There's the focus. The directrix is over here. Make sure you make that a vertical line, x equals 2. This one's a little bit different than number 1 because I didn't tell you directly where the vertex is, but if you've been paying attention, well, hey, that vertex has to be midway in between the focus and the directrix. So right now we know the vertex is at 0, 0. We also know that this is a parabola that's going to open up to the left in order to eat the focus. So it's going to be a y-squared equation. And the distance between the vertex and focus is 2 units. But since we're opening up to the left, I would have you define p as being -2. So if p is -2 and we're opening left in my y-squared equation, y squared would equal 4 times p, which is going to be -8 in this case. And then that's going to be times x. So y squared equals -8x. It's very common sometimes for students to want to square both sides, but squaring both sides will produce a different type of graph. It could be a circle, it could be some other type of conic section. You're only squaring one variable depending on which way this in fact opens. Okay. So let's see if we can just do 2 really quick ones for some last minute practice here. So if I gave you the vertex was at 4, -2, and the focus was at 4, 3. All right, so really quickly, we might want to consider plotting those points. 4, -2 is the vertex. 4, 3 looks like it's up here at the focus. Well, it's going to be a parabola that opens up something like that. I can see that the distance from vertex to focus is 5 units. It's going to be positive since it's opening up. So just know that the difference here is that we don't have a vertex at the origin anymore. When I go to write the vertex at 4, -2, we're going to have, if it's x squared in our equation, x minus 4 squared. Okay. And since we defined p is equaling 5 over here, 4 times that would be 20 times, well, the y coordinate of the vertex is -2, so in parentheses you would have y plus 2. Okay. And you know what, guys? I've run out of space, so we'll call it there for today. I think 25 minutes is sufficient for this particular lesson. So there's definitely a lot going on here with our locus definition. If something was confusing about this, please take the time to look back and review some of the materials in this particular video. In class, you're going to be working on some practice related to all these concepts, and then the next time I see you will be on a review day. So certainly we can catch up on some of these materials then. Thanks so much for paying attention here, and enjoy your time this weekend. We'll catch up with you on Monday on the review day. Have a good one.